Alrighty, Year 12 methods. Hope everyone is well. Let's jump straight and continue again with stationary points, and this particular time looking at the nature of the stationary points. So as you can see here, let's say you had a function that looked like this. You can determine or classify the type of the stationary point depending on what's happening either side of that stationary point. So again, just recall stationary point is where the gradient is 0, there's no slope. So we've got some stationary points listed here. Visually, you can see in this particular case where it's at the top, it's a maximum or a local maximum point. Here you can visually see again it's a minimum or local minimum, and here it's a stationary point of inflection. Yep. Now, how can you actually tell that? Well, as we said, we know the gradient is 0 at each of these points, but what you can then do is look at what's happening or what the gradient is just before the stationary point and what's happening just after the stationary point. So here, if we talk about stationary point A here, what's happening just to the left of it, you can see it's got a positive gradient. As we move from left to right, you can see it's going up in that direction. Here, obviously, there's no gradient, it's just imagine, yeah, that's better. There's no slope there. And after that point, it's going back down again. So it's got a negative gradient. Oop. Yep. All right, so what you can do, you can pop that into a table and you can actually look at what's happening to the shape of it. And as we said, when it is to the left of that point, it's going up in a positive fashion, going up. Stationary point, then after it's going down. Hopefully you can see that it's going like that. It's going to take that type of shape. At the very top, it's going to be a local maximum. Yep. Likewise, the other way around, where just before the gradient, just before the stationary point, we've got a negative gradient. Obviously here we've got the stationary point, and then to the right of that stationary point you can see the slope's going up again. We've got a positive gradient. When you've got a negative, then the stationary point, and then a positive gradient, negative, 0, and then positive, obviously it's going to take that particular shape. Down the bottom here at that stationary point is going to be the local maximum, minimum. Obviously there's the other type as well where you've got the stationary point of inflection. That is where the signs or the gradient is the same on either side. So you can see at this particular point here, with point C, just before it, it's got a positive gradient, and after it, it's also got a positive gradient, positive stationary point, then positive. Okay, it takes that type of shape. You can also have the other version where it goes down, so it's got a negative gradient, then the stationary point, then it obviously negative gradient. It's going to look something like that. Yep. So a stationary point in the middle, or stationary point of inflection there. And you can see how we've done that there. With points A and B, these ones here are also known as turning points, which you can see, rather than the stationary point of inflection like these ones. Alrighty, so this particular exercise is going to ask you to classify what's going on. And so again, you'll need to work out where the stationary point is, and then to work out their nature and actually talk about whether they are a local maximum, local minimum, or there's a stationary point of inflection. You need to look at what's happening just to the left or right of that particular stationary point. Alrighty, so let's have a look here. We've got the function 3x cubed take away 4x plus 1. Again, is asking us to find the stationary point and state their nature. Stationary points, yep. So again, what we need to do is first of all calculate the derivative. Check, we can do that. Yep. It says the stationary points occur when the derivative is equal to 0. Cool, so we're going to make the derivative equal to 0, and we can solve that. In this particular case, we get that at positive and negative 2/3. Yep. So that's where the stationary points occur. Cool. So again, you need to find out their corresponding y values, obviously by substituting in negative 2/3 into the function and positive 2/3 in the function, and here you get where those points are listed there. Cool, so that's where the stationary points are. Now, I would still get in the habit of actually setting up these tables to actually find out what's going on. So I would write down, here we need to find out what's happening to the left and right of negative 2/3. Yep, so I'd pop in this negative 2/3 first of all. We need to find out what's going on to the left, what the slope is, and also what the slope is to the right of that. Yep, so what we're going to do, you can pick any value that's to the left of negative 2/3. Yep. Again, I'd recommend you choose a relatively easy whole number to substitute in. But again, anything that's less than negative 2/3, you can do that, but as long as it's relatively close to there. So in this particular case, they've chosen -1. Yep, that's less than negative 2/3, and they substitute that into the gradient to find out what's going on. Cool, so when you substitute in -1, which is just to the left of negative 2/3, into the derivative, which it will tell us the gradient, we get +5. Yep, so again, 5 is a positive value, which means it's greater than 0. Yep, which means it's a positive slope because it's +5. So again, you know it's going to be positive. The slope of what it actually looks like, positive, as we move from left to right, goes up like that. So that's where that comes from. Obviously at negative 2/3, we know that that's where the stationary point is, so they put that in there. Then we need to find out what is happening just after negative 2/3. And so what they're saying is a number that's just after or to the right of negative 2/3. They say, hey, let's try 0. Yep. So when you substitute in 0 into the derivative, we get -4. Yep. -4 is a value that's less than 0. It's a negative gradient. Yep. So it's going to go down. So you can see at that particular point, around the stationary point negative 2/3, it's going to go like that shape. Yep. So in that particular case, it's going to be a local maximum. Checking out what's happening around this one here with 2/3, we've already done what's to the left of that with this 0. Yep. So the left of that is still coming down. Here's the stationary point. We need to find out what's happening to the right of 2/3. So let's substitute in a value that's to the right of that. They're saying substitute in 1. You could substitute in 2 or whatever, but 1's an easier number to work out. Substituting 1 into the derivative, it comes out as being +5. Again, 5 is greater than 0, so it's a positive gradient. Yep. So it's going to go up like this. Yep. So again, around this stationary point, the shape is going to be like that. With the stationary point down the bottom here, it's going to be a local minimum at that particular point, which is pretty cool. Now it says here, let's sketch this graph. Here's how I'd go about sketching the graph. We know what it's going to look like, where the turning points are. It's going to be a turning point here. It's going to be a turning point there. What they're going to do is also find out where the y-axis intercept is. So we know when you're finding out what the y-intercept is, you need to make x equals 0. So substituting 0 into the function, we get 1. Yep, so it's going to cut the y-axis at 1. So we've got the turning points, we've got that. We've got the y-intercept. We need to work out the x-intercepts. So again, it says here you can use the factor theorem. And they've discovered that x take away 1 is a factor. Yep. So they factorize it as follows. You could use long division to do that. So that tells us here that +1 is going to be one of the intercepts. Yep. That's cool. But then you need to factorize this here to see if there is any other x-intercepts. So to factorize 3x squared plus 3x take away 1, we actually need to complete the square. And you can see what's going on here for completing the square. We get it factorized as follows. Then using the null factor law to make either this bracket equal to 0 or this equal to 0, we come out with these solutions here. For x, plus what we also had x equals 1, as we said before from that factor. So we've got the intercepts, they're listed there. You need to put them onto the graph. So they're there, here, and here. We also discovered it was going to cut at the y-axis, which is there at 1, and we knew the nature of it as it was going, sort of going up here, and it was coming down, and then it was going to turn back around and go like that. So you can see the shape of it, making sure it goes through those points, but also we had the turning points as well from the stationary points that we worked out beforehand. Cool, so there's a little bit involved there, but again, this is achievable. Now the good news is this can be done on a CAS calculator as well. So you can find the value of a function at any point. Yep, you can find the value of the derivative at any point. You can find x and y intercepts. You can also find local maximum and local minimums. Yep. So again, here, I'd encourage you to have a bit of a look through this and play around on your calculator. You can have a so this is a cubic. You can find out the value of y when x equals -4. Again, what they're essentially doing with the textbook is they're saying, hey, put this into your calculator as a function and store that and define it as a function. Then you can just go f of -4 and it will tell you what the value of y is. Yep. The book also goes on and talks about the fact that you can go into your calculator, you can plot the graph, and you can use analysis from the menu. Go G-solve, you actually calculate the x value or the y value. If you wanted to calculate the y value, go y value, and substitute and say what is the x value that you want to find the y value for. It's where you type in -4 and it will put it on there for you and work it out. So it's quite useful to have a play around with as well. Again, what were they asking for part B? Part B, they were asking for the values of x when y equals 0. So again, you've defined the function. You can use the solving part in maths. So when f of x is equal to 0, press the comma, solve it for x, and it will spit out the solutions there for that. Yep, which is cool. You could also do it this way here, G-solve, and do the xcalc, and put in 0 there for that, and it will do it graphically as well. This one here was asking you to find the value of dy dx when x equals -1. Saying calculate the derivative when x equals -1. Cool, so again, you can do it in the math section. You've got the function defined. You can go to interactive calculation and for differentiation, which pull up that. You can say, hey, differentiate f of x, which you defined. And just also putting this little bar here, which is from the Maths 3 section, you can type in, obviously, what you want to calculate the derivative of when x equals -1, and you can type it in like that and it'll work it out for you, which is kind of helpful. So worthwhile checking that out. I don't use this one as often, but again, you can do it using the graphic or the graphing section. So if you have the graphics, the function sketched, you can go into like the little like settings menu, and you can go graph format, and you can actually select the derivative and slope, and you can put set on that. And what happens is, rather than just having the x and the y coordinate, it puts up like this little dy dx, or the derivative at any particular point. What you can do is go to analysis and trace, and you can go to -1 on your calculator by tracing and typing -1. It will go there, and it will tell you on the screen here what the derivative is at that particular point. So you can see it's at -16. So that's useful to know as well. Heaps of calculator stuff today for you to have a play around with. Again, you can find the local maximum using what's called the F max, and actually working through that one there. Again, when you're doing it graphically, if you have this graph up, if you go and you just go to the interactive part and you actually go calculate the maximum, it will come along and find that for you, and also calculate the minimum, and it will do it as well graphically. So probably worthwhile checking that out and playing around with it also. Cool. Worked example number 17 here. It says sketch the following. We've got f of x is equal to e to the power of x cubed. Cool, and so what this is saying is you just need to think about it for a little bit. And as we know, as x approaches negative infinity, so as we go this way, the function's going to get closer and closer to 0. You can get the the y-intercept by making x equal to 0. In this particular case, when x equals 0, this is going to equal 1. Cool. To find out where the stationary points are, again, like we've been doing before, you can calculate the derivative of this and make the derivative equal to 0. In this particular case, when you calculate the derivative of this and you make it equal to 0, it comes out to being x equals 0 in this particular case. Now, what you need to know with this one is, again, after you've got that stationary point, which is here, looking at what happens to the left and right, obviously this is saying as, and this is what this is explaining, it says as the gradient of f is always greater than or equal to 0, it means that this is a stationary point of inflection here. It basically means to the left of this, the slopes, oh, excuse me, have to edit that out maybe. To the left of it, we've got a positive gradient, and to the right of it, we've got a positive gradient. And as we said at the start of this chapter, if you've got the same gradients on either side, it's going to be that stationary point of inflection. Yeah, that's really poor. Imagine that's a stationary point of inflection there. Yep. Okay, worked example number 18. Oh, cool. This time we've got function x log e of x. Here it's asking us again to find the derivative of f of x. We can do this, yep. Using the product rule, it's really x times log e to the x. Yep. So again, you might have to go back and think about how we do that, but we can get the derivative using the product rule. Again, it goes on to say, hey, solve the equation for f of x equals 0. Now, if this equation here, or f of x, was equal to 0, because these are multiplying together, it means either that the x has to be 0, or this log e of x has to be equal to 0. Because remember, 0 times anything like the null factor law is 0. Yep. So either that part's going to be 0, so x is going to be 0, or log e of x is going to be 0. Yep. So they're the only two things that implies. However, the domain is restricted between 0 and infinity. So in this particular case, the only solution that's possible, obviously that's not that one, x has to be 1. Yep, log e to the 1 is equal to 0. Cool, so we've got that one. It says solve the equation f of x equals 0, f dash x equals 0, so the derivative equals 0. So again, you've got the derivative for this here to be equal to 0. This part here would have to be equal to negative 1, because the 1 take away negative 1 is what gives you the 0. So that log e of x has to be equal to negative 1. So making that equal to negative 1, rearrange it, you can find out that x is equal to e to the power of negative 1. Last but not least, it says sketch the graph of y equals f of x. And we've got the information here that allows us to do that. Cool. Some more sine stuff here, and cosine, some trig stuff. Again, you guys can have a look through this. Matter of really looking at what's happening at each of these particular points to work out whether they are local maximums or whether they are local minimums, or it could be a stationary point of inflection in some particular cases. But obviously here we can go through this, have a read through, see that they've checked the sign. Obviously it's that way, that's a local maximum. Here it's a local minimum, so forth and so forth. Yep. Whoops, that's moving around. Well, I can't even draw that last bit there. Cool. So you guys can have a read through that, and I reckon you guys will be all over that. Cool. Oh, bad behavior. Oh no. We knew this day would come where we'd have to have a talk about this, yep. It says, in this course, and in school courses around the world, we deal with functions that are conventionally behaved. Cool, happy days. However, so that really avoids some complications, which is good. However, it says, you've got an example here where of a function which is not in this category. So here we've got this hybrid function, and it says the derivative of this function is defined for all values of x. So this is all real values. It says in any open interval around x equals 0, the graph of this function has infinitely many stationary points, no matter how small the interval. Cool. So you can see that it obviously goes down and gets quite small there. Yeah, that's just a bit of fun fact for you. Don't panic too much about this stuff here. This is the summary section that you guys really need to be focusing on. Cool. A fair bit of information again. I hope you have a good day. Bye for now.